two more. Let's do two more to make us familiar. Okay, so PQ. So this time let's call it R. Okay, so we have a new proposition Rn. It says that n is less than 2 to the power n. And then the domain here. So always the domain are integers. And here the domain are, they are positive integers. So we only consider n to be positive integers. So Rn is the statement n is less than 2 to the power n. So quickly, what is the base case? The basis case is R1. Okay, because we want to show all positive integers are okay. So the base one is naturally choosing the smallest possible integer in this domain. So let's say 1. Okay, so R1, what is R1? R1 is 1 is less than 2 to the power 1. Is it true? Yes, 1 is less than 2 to the power n. So basis case, okay. So it is okay. We just check it using your eyes. Okay. Quickly, we can see that the basis case is okay. So what is the basis case? We are talking about this R1 is true. Okay. Inductive case. What is inductive case? Inductive case, we want to show that. So the inductive case, we want to show that if Rk is correct, then Rk plus 1 will be correct. Okay, so Rk is correct. So we assume that Rk is true. Okay, so we assume that this Rk is true. Okay, so what does it mean? Usually, it is the best to write immediately the conclusion that we have. We know Rk is true, so what does it mean? It means that k is less than 2 to the power k. Okay, and somehow we want to get k plus 1, right? K plus 1. So we know that k is less than 2 to the power k. Immediately, we can write down what? K plus 1 must be less than 2 to the power k, and then plus 1. Am I correct? Right? And then what can we say? Okay. What can we say? We can say that. We can say what? We can say that this is less than, or so this one is less than or less than 2 to the power k plus 2 to the power k. Does that make sense? Yes or no? Is it correct? Is it always correct? No, this is not always correct. When will it be correct? We don't know. Okay, but we know that what we know. Okay, assume that Rk is true. But we will have this one less than this one if what? If yes, k is larger than what? Okay, so k is larger than 1. But we can, okay, but we don't know. We are proving something like this. We cannot say that, okay, k is larger than 1, this is correct. So we are like it's like what? It's like my cooking is delicious. Okay, you understand? So we are saying that this is true. You are saying, okay, 2k, is it true? Oh, okay, yeah, 2k, so okay. So here we are just comparing 2k, 2 to the power k and 1. Okay, so we can say something like k is greater than or equal to 1, and this is true. Okay, good. Yeah, we are not doing something like my cooking is delicious. Let my cooking be delicious, and then my cooking is delicious. So here we are just saying 2k is greater than 1. Okay, it works. Okay, yeah, because it's 2 to the power something. And then 2 to the power 1 is at least 2, and then 2 to the power 2 is at least greater than 2 to the power 1, and so on and so forth. So 2 to the power k must be greater than 1. So here we will have what? We will have this one is equal to 2 to the power k plus 1. Okay? Is that okay? So what do we have? Okay, so the conclusion is we will have rk plus 1 is true if k is greater than or equal to 1. Is that okay? Okay. So we cannot simply say rk plus 1 is true. We will need to say if k is greater than or equal to 1, then rk plus 1 is true in this sense. Okay, so this is a little bit different from the previous one. So what we have proven. Okay, so let's take a look of what we have proven and whether it is still working. So we now know that R1 is okay. And then we also know that for all the possible k that is greater than or equal to 1, Rk implies Rk plus 1. Okay? Is that okay? So we have a new condition here. So it is not about any k. So when k is very small, it may not work. But when k is at least 1, greater than or equal to 1, then it works. Is that okay? Okay. Let's see whether we can use this to conclude what? Okay. So this is what we want to conclude. We want to conclude that for every k greater than or equal to 1, this Rk is correct. Can we do so? Yeah, we can. R1 is correct, right? And then, because it is 1, we can apply this one, because k is greater than or equal to 1. So we have R1, and then R1 implies R2, so we will now have R2. We have R2, we will also have R2 implies R3, so we will now have R3. So in that sense, we will still have everything onwards, from 1, 2, 3, up to infinity. Is that okay? Good. So we have another example. So let's do one more. Okay, the last one. Okay, the last one is, so PQR, okay, so this time let's call it S. Okay, Sn. Sn is like this. N cubed minus n is divisible by 3. And let's say we assume that the domain of n, they are all positive integers. Okay, so if the domain is all positive integers, then the basis case will be S1, right? What is S1? S1, take a look. 1 cubed minus 1. 1 cubed minus 1 will be 0. Is 0 divisible by 3? Yes, okay. So what is meant by divisible? If a number is divisible by 3, it means that there exists some, so if a number x is divisible by 3, it means that there exists some integer k such that x is equal to 3 times k. So this is meant by divisible. So in that sense, 0 is divisible by 3 because 0 is equal to 3 times 0. Okay? Okay, good. So S1 is true. We can check it. And then for the inductive case, we will assume what? We will assume that Sk is true. So Sk is true, it means that k to the power 3 minus k is equal to 3 times some m for some integer m. Okay, so this is meant by k cubed minus k is divisible by 3. Is that okay? And now we are interested in what? We are interested in k plus 1 cubed minus k plus 1. We are interested in this one. We're interested in this one. So what should we do? Okay, so what should we do? Expand it. So let's expand it. So what is k plus 1 cubed? So it is k cubed plus 3k squared plus 3k plus 1. Is that okay? And then minus k plus 1. So it is minus k minus 1. Is that okay? Good. So this one and this one can cancel each other. Okay. This is a multiple of 3. This is a multiple of 3. And this k cubed minus k is a multiple of 3. So if you do some simplification, this will be equal to 3 times m plus k squared plus k. Is that okay? So it implies that sk plus 1 is true. Okay, so again, we are using induction, and then we prove this argument Sn is true for all possible positive integer n. If you are okay up to this point, could you please raise your hand? Okay, excellent. Okay, but for this one, so every proposition, there may be more than one proof. Okay, and we can have a very simple proof for this one. Rather than using induction, we can use factorization of n cubed minus n. So n cubed minus n is equal to what? It's equal to n times n squared minus 1, right? N squared minus 1 is equal to n minus 1 times n plus 1, right? So this is equal to n minus 1 times n plus 1. Is that okay? Okay, so what's so special about these three things? N minus 1, n plus 1. They are consecutive integers, right? So one of them must be divisible by 3. So there are 3 of them. One of them has to be divisible by 3. And you can actually strengthen this argument a little bit. So you can make this 6. Because for any 3 numbers that are consecutive, one of them has to be even. Okay, so you can actually know that n cubed minus n is divisible by 6. Okay, good. Okay, now, okay, so for induction to work, it is not necessary that we are proving that it works for all integers. Sometimes you may start with a different basis case. It depends on what are the arguments that you are going to show. Okay, so let's have this new argument t. Okay, let's say Tn. Tn is 2 to the power n less than n factorial. So n factorial is n times n minus 1 times n minus 2 up to 1. Okay. But if you check, if you substitute n is equal to 1, what you will have? You have 2 to the power 1 is less than 2 factorial. Is it true? Or is it, 2 to the power 1 is less than 1 factorial. Is it true? No, it's not true. Okay. Even when n is equal to 2, let's say when n is equal to 2, 2 to the power 2, is it less than 2 factorial? No. How about 2 to the power 3? Is 2 to the power 3 less than 3 factorial? No. Okay, but here we want to show that the domain of n we are interested is the numbers n can be equal to 4, 5, 6, 7, and all the integers afterwards. We actually want to show that this proposition is true for every n greater than or equal to 4. Okay? So what should we do? What should we do? So we will use a basis case like, so we do not start our basis case as 1 because we are not proving 1 is correct. When n is equal to 1, it is wrong. Okay, but the first case that we are interested is when n is equal to 4. Is that okay? So we start the basis case as T4. Is that okay? T4. Okay. So T4 is what? T4 is the statement 2 to the power 4 is less than 4 factorial. This is 16. This is 24. Correct. So this is true. Okay. So here the inductive case will be So we can actually strengthen the inductive case because we are not interested about n is equal to 1, 2, 3. Okay, so we can consider only the k that is greater than or equal to 4 and assume that P, so this is Tk is true. So if we assume that Tk is true, then we will have, so we will have 2 to the power k is less than k factorial. Is that okay? And now we are interested in what? We are interested in the case t of k plus 1. So we are looking at 2k plus 1 here. And 2k plus 1, we can use this to help us to simplify it. So this is equal to, so first of all, 2k plus 1 is equal to 2 times 2 to the power k, right? Okay? And 2 to the power k is less than k factorial. So it is less than 2 times k factorial. Is that okay? Is that okay? And so this must be less than k plus 1 times k factorial. Is that okay? Because we are considering k to be greater than or equal to 4, so k plus 1 will be greater than 2. Okay? So we can have this argument to be correct. Okay, so this is what? K plus 1 times k factorial is k plus 1 factorial. So at this point, we have shown that 2 to the power k plus 1 is less than k plus 1 factorial. Okay? So this implies t k plus 1 is true. Okay? So far, so good, right? Okay? Okay. Okay, so we have still some time. Let me see. Okay, not enough time to so here, this is one form of induction. But there are still some other forms of induction that I want to introduce to you, maybe on Monday. Okay, so here, so this week, go home and complete this assignment 2. Maybe some of the questions you still do not know because I'm still missing a certain part of induction proof in this lecture. Okay, so you try your best to do. Okay, okay. Now let's do something interesting. So last time, I want to give you an example of a wrong proof and see if you can find out the mistake. So now I'm drawing any arbitrary triangle. So I'm drawing any arbitrary triangle. But I want to show that this triangle is isosceles. Okay, isosceles triangle. So what is isosceles triangle? A triangle that has 2 legs of equal length. Okay? But this is clearly wrong because I'm drawing a triangle. I don't draw it on purpose that it is isosceles. But now I am showing that every triangle is isosceles. And if you believe my proof, I can actually show that every triangle is equilateral. It means that all the sides has to be of equal length. Okay. Okay, so let's see my proof. Okay, so here, first of all, I have an angle. So this is A, B, C. Okay. Okay, so I pick one angle and draw an angle bisector here. So making these 2 angles to be equal. Is that okay? And from this BC, I draw what we call a perpendicular bisector. So that divides this part to be the same length as this one. And this is the right angle. Is that okay? So these 2 will meet at a certain point. Okay. So I join this and I join this. So far so good, right? Now, the next thing is I'm going to draw what? I'm going to draw 2 perpendicular lines in this triangle. Okay, so I call this point, let's call this point P, let's call this point Q. Is that okay? Is that okay? Now look at this triangle. I'm claiming that this triangle and this triangle, they're the same. They're congruent. They're the same. Why? Okay, these two angles are the same, right? These two angles are the same. So that means that these two angles are the same, right? Okay? Now you have two angles the same and one side the same, so they are congruent. This is ASA, right? You have angle, side, angle, angle, side, angle. Is that okay? Is that okay? So we now have this line is equal to this line. Yo. Okay. Ayo. Okay. 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 These two are the same. Okay. Now next, let's look at this triangle and this triangle. Okay. This triangle have this side in common. They have a right angle here, and then this side they are common. So this time it is SAS. Okay, SAS, right? SAS. So that means that this line and this line, they are the same. Is that okay? Good. Okay, good. And then what? Okay, and then still recall. I hope you still recall. We are saying that this triangle is the same as this triangle, right? So that means that this line is the same as this line. This one is the same as this one common, so this one is the same as this one. Is that okay? Good. Now, so these two lines are the same. Let's look at this triangle and this triangle. They have the height the same, the slant side the same, and a right angle here. So there is something called what? RHS, right? Right? RHS, right? So right angled, the what? Yeah, perhaps the height and the slant. Okay, so RHS, or a side and the hypotenuse, or whatever. Okay, yeah, right angle, a side, and one of these is it called hypotenuse? Okay, so RHS, whatever. So what does it mean? It means that this line is the same as this line. Am I correct? Is that okay? Okay, good. Look at AB. AB is a green plus a yellow. AC is a green plus a yellow. Isosceles triangle. So they are isosceles. Now, if you believe my proof, I can duplicate this proof by choosing B as an angle bisector and finding whatever line as the B angle bisector in perpendicular bisector, and then we can show that these two lines are also the same. So that means that every triangle that we can draw, it must be equilateral. All three sides are the same. Okay, there is something wrong. Where it is? There must be something wrong. Yeah. Yes, yes. Very good, very good. Okay, he has made the point. So here I'm tricking you. I'm assuming that the intersection of this one and this one lies inside the triangle. But I'm tricking you. For most of the cases, it is not lying inside the triangle. You understand my point? Okay, if it is not inside the triangle, then everything will be different. Okay, so in that case, maybe it's like here. So in that case, Q will be something outside the outside C, but P will still be something inside AB. So in that case, so you have something like AP, PB is equal to something like AQ, QC, but then this QC is something over, something like this. So you go home and draw and repeat this proof. Okay, so you can do this. Okay, ask your friend. Okay, so again, you just need to do what? You have a triangle, whatever. One of them is angle bisector, and then the other is a perpendicular bisector. You start with something like this, and then you can get arguments. Try it by yourself. and then see if you can repeat this proof and find out the mistake if you draw it correctly. Okay, so it's about time to end the class now. Okay, so let's meet again next Monday. We will have a tutorial on assignment 2.